Hello, today we're going to show how easy it can be to take model-based designs created in Simulink and deploy them at the TwinCAT real-time execution system running on proven industrial hardware. In our demo today, we will start with a Simulink model designed for basic servo motor control. We will then deploy this model to a TwinCAT real-time and then link this model to a servo drive that's being controlled via the EtherCAT field bus. Let's get started. Here, we are in Simulink with our servo motor control model. The drive control block has some simple inputs, including the drive status word, drive enabled, a velocity multiplier, the desired set position. As output, we have the drive control word that will be sending commands to the servo drive. Now let's step into the drive control block. We see a small state machine or state flow diagram that controls the various states of the servo drive and transitions the drive from a not ready state through the state machine to a ready and operational state. Once it's in this operational state, commanded position variables are passed to the position controller block. And in the position controller block, there is a basic position control loop. Now, let's take a look at the model setup. First thing we'd like to do in the model parameters is set the model generation to be a TwinCAT target system. Looking into the system target file browser, we see the TwinCAT target system. Selecting the TwinCAT target will make it the active target for the model code generation. We see that we get multiple options for generating this target system, with things like assigning a vendor name to the model, assigning version number, and many other options. The platforms we'd like to deploy this on, whether it be a 32-bit or 64-bit, certificate signing, or even the protection of the model intellectual properties, or IP. Other option of building a PLC library and auto-installing that PLC library. This means that a traditional PLC programmer can use and interact with the model in the PLC by only needing to access a standard PLC library and function block, as they are already very familiar with. With basic parameters set up, we can then go to the Simulink coder and generate the code. Once the model is finished building, we can step over to the TwinCAT development environment. We can very easily add in generated Simulink code. If we have a look here, we see an object that was created called the MATLAB Expo, and this is our position controller model. Bringing that in, we can see that we rebuild and display the block diagram here inside of the engineering software, so we can really get a good representation of what the model looks like. And we see the same passing in of the parameters and same passing out parameters. Here, I'd like to point out a couple of things. First is, we don't need to modify the Simulink model for it to be able to use inside of TwinCAT. We can use the existing model, the existing structure, and the standard inputs and outputs. Here, we've structured this model in such a way just to make it very simple and easy to understand. Top overview. The other thing I'd like to point out is, at the top, we can see the red text that says this module is for non-commercial use only. This is because the engineering tool here can be used for free with limited functionality, meaning you can download and try out all these tools for free without needing to first purchase a license. Now, the inputs and outputs that were set up in the model now become inputs and outputs to this model here, which can link to other programs, such as PLC or C++ programs, or directly to I/O, or even motion control or analytics. We can step through the model by going to the drive control block. And stepping inside, we see our state machine, and we can step back and forth between the drive and the parameters. The parameters for startup, or the different blocks, are all available on the side. And now, we'd like to link this model to actual hardware. I'm currently connected to a small machine here, or a training station, and what we'll do is scan in the servo drive. We see those two motors and we'll scan in the servo drive and motor hardware. So very simply, I can choose Scan and it will go find the motors and the I/Os that are attached to the controller. Now we can see multiple I/Os for inputs and outputs, for analog, digital, even safety. And of course, Here we see that we have a servo drive. Now we can very quickly link this data between the servo drive and our Simulink model. Okay, now that everything's linked between our hardware and the model, we need to then add this to a real-time task so we can execute it within the real-time environment as a cyclic update. In our case, we'll execute the model every 5 milliseconds. And we tell it which tasks to update with. Now we can run this code on the device. Now that the device is running, we can see a live view of the input data and the output data from the model. Here we will add a velocity multiplier, a set position, and we will tell the drive to enable by setting that to true. And we can see that the motor is running. If we flip back to the block diagram, we can see that we have an output status to the drive of 15, telling the drive we would like to go to position 10,000, and here's the degrees to increments that we're commanded motor with. During the build process in Simulink, we've also generated a PLC library for those who would like to call the Simulink code from a more traditional ladder logic or structured text PLC environment. Here we can see we can very easily add the reference. Here's the Simulink target we build from the MATLAB Expo. And as soon as we add this in, we can see that graphically we've built a POU or a function block that can very easily interface with the Simulink module with some simple inputs and outputs from PLC. Thank you for joining us, and for more information contact us at www.beckhoff.com.